Hi, I'm Aidan. I'm the model release team lead for ACCESS-NRI, and we are focused on providing reliable, replicable and reproducible climate models for the community. And these are my team who've been involved in this work. I started out, I spent about 8 years supporting ocean models in a couple of different centers of excellence. And these were two things that came up, two quotes from meetings approximately. Do you have the good binary? Did you use the bad aerosol file? So in this case, the good binary was one that worked in a simulation but could no longer be recompiled again. So from my perspective, if you can't reproduce something, you're not doing science. I'm not sure what it is, but it's not science. And did you have the bad aerosol file? They knew that it was a bad file, but there weren't the tools to track what was going in and out of the models. And I don't blame the scientists. These are difficult problems, and they just didn't have good tools. So I spent about 8 years trying to improve some of that stuff, and now I'm at ACCESS-NRI, and hopefully we're going to be doing it even better. So the design goal here is that scientists can trust that any variation in a climate model is due to factors under their control, rather than changes in software, dependencies, or the tools used to build the model. So this is important. Basically, I want you to be able to do your jobs and not have to worry about all the boring technology stuff behind the scenes. So reliability, reproducibility, replicability. What's the problem? Well, it's difficult to reliably build climate models, reproduce results, and so replicate scientific findings. And why? Well, climate models are an imperfect translation of extremely complex scientific understanding into computer code. And what's more, they often comprise separate different models of the Earth system with varying standards of software engineering and architecture, independent build systems, different dependencies. They run independently and just exchange information at the boundaries. So it's quite a challenging environment to work in. On top of that, they're computationally very complex. They require very high performance computing resources, and from hundreds to tens of thousands of CPUs, and so that means building and running those models in a very specialized environment. So at ACCESS-NRI, we are leaning very heavily on a tool called SPAC. It's a build from source package manager targeting high performance computing. It's developed at Lawrence Livermore. So why SPAC? Well, it's build from source. So we build exactly what is required, and that's important in science. You guys have very exacting requirements of the dependencies and software you want to build. So you can't really use just sort of generic off the shelf. It's a package manager, so that means we can programmatically orchestrate builds, automatically build and locate dependencies, install and track multiple builds, get build provenance and build reproducibility from this system. So the build provenance is very important, and because it's a package manager, it knows exactly what went into every build, and so you have that provenance and that reproducibility, and you can build it again. And it targets HPC, so it was developed at Lawrence Livermore and you can operate within an existing HPC system. You can use those components that are very important and have been optimized by the HPC staff and still build the other components that you want and need. So this looks a bit complex, doesn't it? So a model has separate components. So in this case, each of our models, this representation, they're all in GitHub repositories. They have a SPAC package that sort of wraps the model so that we can interface with SPAC, and it can build whatever it needs to do, and you just define what dependencies you need. And then we have build CI around that as well, so checking the code correctness by compilation CI, and that's all enabled by SPAC. And so we have a model repository or deployment repository is just a SPAC environment that defines what version of the model and the version of the dependencies that are in it. And then if we want to update that model, we do it via a pull request. You make a fork, and then you make a change, and then you do a pull request. And importantly, each of these commits into the pull request builds a separate environment of the model on Gaudi. And every time you do another commit and it adds to the pull request, that is automatically builds in another environment. All those environments are accessible all the time until you merge the pull request or delete it. So that means as a scientist, you can make incremental changes and compare between different versions with as you go along as your staged pull request. So this is a pre-release environment, and then once you're happy with it and it's merged, all those get deleted, and then it gets merged into the main and built on Guardi and then deployed on Guardi and accessible via modules. So that's the system that we've built, and it's working pretty well. And part of that also is we now have a build database as well. All our released builds are in a database where we can look up everything that we've built and released, and we intend to make those sorts of interfaces more visible to the community in the future. So, just recapping, with SPAC has some implications because of the way it works. There's a low marginal cost of building and deploying software, so we can build and deploy as many versions with as many dependencies as we like. Once you've done it once, you can do it 100 times, you don't really care. It's a computer does it for you, right? It's cross-platform by design, so that enables easy replicability. It can build on an HPC, on Amazon EC2 runners and different hardware. It just works. And generic programmable builds means that we can make plug-and-play tools. So we've created reusable compilation CI GitHub actions. This is borderline magic as far as I'm concerned, and created reusable deployment GitHub actions as well. So these are just reusable. They just plonk them into a new repository, bang, it all works. We don't care what's being built because we're using SPAC, and it's plug and play. And that enables us to scale our efforts. We really want to support what the community needs, and that could well be upwards of 20 different models, who knows, but we can't do it without tools like this. So this is another complicated diagram, but it's just trying to show you, this is how model configurations are updated and versioned. So here, so what we've decided to do is use a sort of major-minor versioning for our configurations. So every commit into a configuration repository is tagged with a version. So it's either, and it's major minor, so in this 2.1, 2.2, and as soon as you have a configuration that breaks reproducibility, then we update the major version. So as a user, if your major version matches, you can upgrade your configuration. If it changes, then you no longer have reproducibility. That may or may not be important to you, but we have that information available. And then we have a whole workflow for adding in changes. We have QA checks. These reproducibility CI checks are done on NCI as well. So this is all to make the configurations higher quality for you and make it clear when we break reproducibility. So as an example, the ACCESS-OM2 model was our first major release in 2023. We took over support of that from Cosima, and since then we've now supporting all 12 configurations, global 1 degree, quarter degree, and 10th degree, 2 forcing products and a BGC and non-BGC. We've had 2 release updates since and bug fixes. These are all deployed automatically on Guardi. We have full build provenance. The module versions are selectable through the module system. And we've had a bunch of updates for PyU for syncing and reproducibility. And hopefully the intention is this will make a more reliable service for you as users. And so what's next? Well, end-to-end provenance is our final goal, and we're working towards that. So we've got build provenance with SPAC. We have the database of our model builds and deployments. We are auto-generating unique experiment IDs in PyU and embedding those in metadata. The model inputs we're tracking them all. We don't have good provenance on some of the historical inputs, so that's maybe an unsolvable problem currently, but in the future not so much. And model outputs, tracking of those is something we're working on. A database for experiment metadata is something we want to get into, and we've done some prototypes and things. And ideally a web interface to query all levels of experiment provenance is the final goal. Just in summary, reliability, reproducibility, replicability, we've gone a long way down the road in a lot of those cases, but we've still got more that we want to do for you. Thank you.
Thanks, Aidan. Questions from the audience? Yeah, Ed.
Thanks, Aidan. Obviously, I love these tools. It's amazing. What if somebody wanted to take one of these binaries and run it in a different style? So they wanted to use ACCESS-OM3 numerics, but run it in a world with different continents or a rectangle or something like that. How would that fit into this sort of workflow?
Well, if you don't need to recompile, then you're good, right? So in terms of developing new configurations and things like that, yeah, I mean, that's something the community just has to ask for. And Tommy's already working on a design for version 2 of this system to improve some of the features for the model development team so they have more flexibility. So, we can design things, we just have to know what the parameters are and how we need to go about that. So just let us know if you have needs and we'll see what we can do.
Yep, over there. Just wait, yeah.
Thanks. So following on from that, SPAC looks great, but there's clearly a risk of it producing just a plethora of modules. What do you do if your model is configured at compile time, not run time? I'm thinking specifically of WaveWatch. Like if you're going to have a separate build for every time you want to alter the physics in WaveWatch, you're going to end up with potentially hundreds of modules.
Yeah, it's a good point. I guess I'll have to talk to Elil about that. You can support a smaller subset with sort of variants and things. The modules isn't such a big deal. That's sort of configurable about what you want to expose and what you don't. And what we end up doing is having a top-level module because we have this build environment. That's the thing that people load, and it auto loads all of this stuff underneath, so you don't really care about it. So I'm sure there are technical ways we can get around it. Probably, yeah, there'll be some trade-offs, I suppose. But yeah, happy to talk about it.